Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, good evening formally to my grade 12s, okay? Welcome to this evening session, okay? Last week we came through a formal teaching of the photoelectric effect, okay? And what we have to do now is just make sure, okay? It's just make sure that this is consolidated with a couple of exam papers, okay? Little secret, okay? So you remember and don't forget, I matriculated in 2013, and this is my 2013 November paper for physics that I wrote for 3 hours in a cold school hall. Even though it was summer, it was still extremely cold. I wrote with a blanket around my legs, and I had long pants on, and I had long socks. So you can imagine how cold that hall was, okay? Don't even get me started on the June and the September exams. It was even colder. Alright? It was even colder. Anyway, I think my marks in June were slightly higher. I don't know, I can't remember. Yeah, actually they were. My June mark for physics was absolutely sweet. I had a fantastic June holiday because I did so well. Anyway, question 11. There were only 11 questions. This is the photoelectric effect question. It's the final question of your paper 1 exam. Let's read it together quickly. We won't go through all the questions because you all can read that, but let's just introduce the question for everybody watching. In the simplified diagram below, light is incident on the emitter of a photocell. The emitted photoelectrons move towards the collector and the emitter registers a reading. Okay, now, you got 3 questions there that you can actually see, because if I scroll too far down, you'll miss the diagram as well as the information. Okay, so we're going to start with 11.1.1 all the way up until 11.1.3. So that is 1, 5, 6, 7. That's going to be about just under 10 minutes. So it's now 10:02, roughly just about 10:02, so I'll round off. So that means at just before the hour of 7 o'clock, this will be done. So maybe at about 7:57 or 7:58, we'll give this a mark. Okay, let's go, guys. Let's do this one. Well, only one thing left to do now is that we are done, is to go and mark it. So name the phenomenon, of course, 11.1 that is illustrated above in that question. That's obvious, guys. It's the photoelectric effect. Don't even have to write it down, but I will. Okay, that's the photoelectric effect. Awesome. 11.1.2, not 11.2.1, so let's fix that. Okay, the work function of the metal used as emitter, we're not told, is 8, 0 or 8 times 10 to the negative 19 joules. So before we go further, let's just denote that the work function is equal to 8, 0 times 10 to the negative 19 joules. The incident light has a wavelength of 200 nanometers. So lambda 200 times 10 to the power of negative 9 meters. That's what nanometers is in, alright? And calculate the maximum speed, alright, sorry, let me read that question again, I've got mixed up my words. Calculate the maximum speed at which an electron can be emitted, okay? This is going to bring in the formula E is equal to W0, which is the work function, okay, plus EK max, okay, or just EK. Now, this is going to equal, of course, you can specify what you want to change E into, okay. You can say, well, I know that E is equal to HF, okay, so over here, you know E is equal to HF, but F is equal to C over lambda. So therefore, E can also equal to H times C over lambda. So we can put that in here. Something went wrong there. hc all over lambda is equal to the work function plus half mv squared. Okay, and now we can go ahead, put a squared there properly. Okay, now we can go ahead and substitute. Well, Planck's constant, 6,63 times 10 to the power of negative 34. I'll put this in brackets. Times the speed of light in a vacuum, 3 times 10 to the power of 8. Okay, all over 200 times 10 to the power of negative 9 is all equal to, just section this off here, because this is our side note, writing down everything that we know, is equal to the work function, which is 8 times 10 to the negative 19, okay, plus half. Now, what are we adding here? Mass. What's the mass of an electron? It's on your formula sheet. 9,11 times 10 to the power of negative 31, okay, multiplied by v squared, which is unknown. Okay, v squared is unknown. Okay, so don't worry, we'll fix this little mess up in just a moment. Let's just do this option on the left hand side here quickly. Okay, so 6,63 on top there, let's just bracket it out nicely, times 10 to the power of negative 34 multiplied by 3 times 10 to the power of 8 all over 200 times 10 to the negative 9. So we should end up on the left hand side with 9,945 times 10 to the negative 19. Alright, and that should equal everything over here, so that's 8 times 10 to the negative 19 plus what is half of 9,11? So let's take half. 9,11 times 10 to the power of negative 31, and we'll get plus 4,555 times 10 to the negative 31 brackets v squared. Okay, so you see we've got the same exponent here, so 9,945 minus 8 will give us here 1,945 times 10 to the negative 19 is all equal to 4,555 times 10 to the negative 31 v squared. Okay, if we divide both sides, so 1,945 times 10 to the negative 19 divided by 4,555 times 10 to the negative 31. Okay, we'll get a massive number of 4,27000. I'll just round it off to 2 times 10 to the power of 11 equals to v squared. If I square root both sides, I'll get what v is equal to. Okay, so the whole number there is 4,270032931. So if I square root that answer, I'll get, if I have to scientific notate it, 6,53 times 10 to the power of 5 meters per second. And if I just enter the calculator's answer doesn't give me this answer. It actually gives me 654,8899, so that's 89 meters per second as the speed that the electron can be emitted at. Okay, scientific notation a little bit shorter, otherwise just entering the entire number in like that. 653,454,89 meters per second. Quite a big number. Okay, and that was 11.1.2. 11.1.3 says incident light of a higher frequency is now used. Now, obviously we haven't calculated the frequency on its own, but we can because we got the wavelength and we know what the speed of light in a vacuum is. How will the change affect the maximum kinetic energy of the electron? emitted in question 11.1.2. So we found the speed, maximum speed. So we can obviously also calculate the kinetic energy if we were asked to. We're not asked at the moment. They just want us to write down increases, decreases, or remains the same. Well, if I use a higher frequency, okay, then that means, because speed of light is a constant, then if a higher frequency, I must probably have a lower lambda. All right, or shorter wavelength. The shorter wavelength means higher frequency. Longer wavelength means lower frequency. So a high frequency means shorter wavelength. So a wavelength must be shorter than 200 nanometers. So if I have a wavelength shorter than 200 nanometers and I have a higher frequency, then that obviously is going to increase my energy, which is my E equals hc over lambda. That value is obviously going to increase. Okay, my work function will probably remain the same. Okay, but that's going to remain, but that's going to increase. So therefore, I've mentioned increase quite a bit. So the answer for 11.1.3, because if you use a light with higher frequency, that's actually going to increase your kinetic energy. So the answer there is increases. 11.1.4 now says the intensity of the light is now increased. Okay, how will this affect the speed of an electron calculated in 11.1.2? Okay, well, we must understand, what does intensity affect? Intensity only affects the number of photoelectrons emitted per second. Okay, intensity doesn't have anything to do with the speed. Okay, so the only two things that can affect kinetic energy is either the frequency or the wavelength of the incident light. That can only affect the kinetic energy. And the kinetic energy involves speed. So the answer for 11.1.4 is it will remain the same. The speed will not be affected. Okay? Because intensity only affects the number of photoelectrons emitted per second. So it'll have an effect only on the number of photoelectrons that are emitted. Maybe if you increase the intensity, maybe not one, but maybe 2 or 3 electrons might be emitted. But the speed will remain the same. So the answer there, it remains the same. Intensity only affects the number of photoelectrons emitted per second. That was the explanation, and so are 11.2 and 11.3. 11.2 says a metal worker places 2 iron rods A and B in a furnace. After a while, he observes that A glows deep red while B glows orange. Which one of the rods, A or B, radiates more energy? Give a reason for your answer. Okay. Well, the answer here, ladies and gentlemen, is B, the orange. The rod that glows orange. Why is that the case? Well, orange light, if you remember your light spectrum, orange light actually has a higher frequency than red light. All right? It has a higher frequency than red light. Now, you could obviously have explained it the other way, saying that while it's still B, the orange light has a smaller wavelength than red light. So your red light actually has your low frequency and longer wavelength, or your longest wavelength, but if you go more to the orange side, it actually has a smaller wavelength, all right, but a higher frequency. So that answer there is definitely rod B. So you could just mention B. The last question, 11.3, neon light illuminates many buildings. What type of spectrum is produced by neon signs? And that's the line emission spectra. Okay, something you just had to learn from your notes. It's just the line emission spectra. Okay. And that was the 2013, my final exam on the photoelectric effect. Right, grade 12s, try another paper, 2014. Okay, just the year after. Question 10, this one, ultraviolet light is incident onto a photocell with a potassium cathode as shown below. The threshold frequency of potassium is given as 5,548 times 10 to the 14 hertz. Okay, I'm going to scroll down a bit, As you can see, we have some questions there. Now I know you all can read, so I'm going to say let's do 10.1 all the way through to 10.3. That should take us roughly 8 minutes, but I'll give 10 just for some 2-minute leeway, and then we'll mark this one as well, and we'll go all the way through till 10.4. Well, 10.4 we actually can do, so let's actually say 10 minutes, even though it's 11 marks. Let's actually make it 11 minutes, because you just have to explain your answer in 10.3. That's all 10.4 question is, just explain your answer. Okay, let's go for this one. Okay, let's go through. Define the term threshold frequency or cutoff frequency. So basically we should understand, if I paraphrase it quickly, just rule off here. It's basically the minimum, so it's not the maximum. The only definition that has the word maximum in it is cutoff wavelength. Okay, so this is 2014 November, paper 1. This question 10.1, it's the minimum frequency. Basically the minimum frequency of a photon, okay, or just the minimum frequency needed to emit electrons from the surface of a metal. Surface of a metal. Awesome. Right, 10.2. Calculate the the maximum speed of the ejected photoelectrons is 5.33 times 10 to the power 5 meters per second. Calculate the wavelength of the ultraviolet light used. Okay, so again, we're going to use the I'm going to go straight to the formula HC over lambda. Okay, I'm going to go straight there because they want to know the wavelength. That's the formula that has wavelength in it, is equal to the work function plus half mv squared. If you want to put E equals the work function plus EK and then substitute into this, that's fine. Just note, you're only going to get a mark basically for either one of them. You're not going to get a mark for both of them. I'm going to run out of space here, but see how much we can fit in. So we're going to have 6.63 times 10 to the negative 34 brackets here, all over lambda, 3 times 10 to the power of 8. That's equal to the work function. Now the work function formula is also H times F0, and we were given the threshold frequency. Okay, remember W0 is also equal to HF0. So we're given the threshold frequency, so we're going to have to say use this formula in place of that. 6.63 times 10 to the negative 34 brackets times 5.548 times 10 to the power of 14. Okay, plus half mv squared, half the mass of an electron, 9.11 times 10 to the power of negative 31. Okay, all multiplied by the speed, which they gave us there, which was 5.33 times 10 to the power of 5 all squared. Okay, take a mental picture of that, because it's going to disappear. Okay. In fact, let me put these, okay, let me just perform the calculation first. Okay, so the numerator on the left hand side, 6.63 times 10 to the power of negative 34, alright, times 3 times 10 to the power of 8. Okay, that should give me up top here 1.989 times 10 to the negative 25 all over lambda. Okay, let's make that visible again here at the bottom. So let's calculate this part here. 6.63 multiplied by 5,548 times 10 to the power of 14. Okay, we're going to get quite a big number. I'm just going to round it off to 2 decimal places, so that's 3,68 times 10 to the power of negative 19. Okay, and plus, I can do this one on my own, I think. Half of 9,11 times 10 to the power of negative 31, all over, oh, not all over, times 5,33 times 10 to the power of 5, and that was all squared. So that's plus, sorry, I got a mosquito flying around my head. I got it though. No, I didn't. I lied. 1,29 times 10 to the power of negative 19. Okay. So this can obviously be added. So we'll end up with a value here. So this is going to equal 1,989 times 10 to the power of negative 25 all over lambda. That's going to equal, so let's maybe take this plus, or let me just do that whole thing again here, times 10 to the power of negative 31 multiplied by 5,33 times 10 to the power of 5 all squared major bracket. That should give us a total answer here of 4, I'm going to round it up to 3 decimal places because I have 3 decimal places there. 9,702 times 10 to the power of negative 19. So obviously if I multiply both sides by lambda, and then I divide both sides by this number, which is 4,972 times 10 to the power of negative 19, these will cancel on this side. And then I'll have 4,972 times 10 to the negative 19. And therefore, after all this work, most of it is just writing most of these things out. It's not even a lot of work, really. I'll have 1,989 times 10 to the power of negative 25 all over that answer. And we should end up with 4,000. So that's basically just 4 times 10 to the negative 7, and lambda wavelength is measured in meters. And that's our final answer for 10.2. For 10.3 and 10.4, the photocell is now replaced by another photocell with the rubidium cathode. The maximum speed of the ejected photoelectron is 6,10 times 10 to the power of 5 meters per second when the same ultraviolet light source is used. How does the work function of the rubidium compare to that of potassium? Write down greater than, smaller than, or equal to, and the answer there is smaller than. Okay, let's explain why. Okay, now y is for 3 marks. Okay, so I'm going to combine 10.3 and 10.4 in one question. Let's just use a separate page for that. So 10.3 and 10.4. Answer is smaller than. I think that was the option, or I think it was smaller or less than. Okay, and the reason is that the wavelength, I wanted to cheat and say lambda, but let's rather write out the word since it's an explanation. The wavelength, or the frequency, or the energy, let's rather say frequency, wavelength, or frequency, or energy of the incident light will remain constant, or remains constant. Okay. However, since the speed is greater or larger Okay, since the speed is greater, okay, the kinetic energy, okay, is bigger or larger. Okay, and the work function, so I'll shorten this one now, W0, or the threshold frequency, is now smaller. And there's your 3 marks. Okay, since the speed is greater, the kinetic energy will be larger, and the work function or the threshold frequency is lower or smaller. Okay, so to answer the question one more time, how does the work function compare to that of potassium? Okay, greater speed means greater kinetic energy, but smaller work function or smaller threshold frequency. All right, here we got a 2016 November paper. Quite a nice question, a question with a difference. They give you a graph of kinetic energy, EK max versus frequency, okay, in times 10 to the 14 hertz. Okay, a learner investigated the photoelectric effect of 2 different metals, sodium and silver, using light of different frequency. The maximum kinetic energy of the emitted photoelectrons is plotted against the frequency of the light for each of the metals, as shown in the graphs below. Okay, now again, define the term threshold frequency. We just defined it earlier, so I'm not going to have you answer that question. However, question 10.1.2 and 10.1.3 we can go ahead and answer, as well as 10.1.4. Okay, so that shouldn't take us longer than, let's see, 3, 4, 5. That shouldn't take us longer than 5 minutes. Okay, because I think there's a bigger question at the bottom here. Okay, for 10.2. So let's just spend 5 minutes on this. We'll answer the questions, and then we'll come and spend the remainder of the time on 10.2. Okay, without wasting any more time, let's go. So let's just go through question 10 here. We've already defined threshold frequency as the minimum amount of frequency to be able to emit electrons off the surface of a metal. That's for the threshold frequency. Table 1.2, which metal, sodium or silver, has the larger work function? Okay, explain the answer. Well, definitely looking at the frequency values here, I'm going to say silver, and the reason why is because the threshold or cutoff frequency is definitely higher. Okay, it's definitely higher. Okay, even though that's not the threshold frequency in hertz, okay, it's just its frequency. Okay, but the frequency is definitely higher. Another way to explain it is like to eject electrons with the same kinetic energy from each metal. Light of a higher frequency is required. All right, then hence for silver, so light of a higher frequency would be needed to emit an electron off the metal silver. Hence, the work function would definitely be larger for silver than for sodium. Table 1.3, the physical constant represented by the slopes, that's Planck's constant. 10.1.4, if light of the same frequency is shone on each of the metals, in which metals will the ejected photoelectrons have a larger maximum kinetic energy? They'll definitely be sodium. Smaller frequency, right? Remember? Smaller frequency, which we dealt with earlier on, has maybe a shorter frequency, a lower frequency, larger wavelength. Okay. 10.2.1, which is definitely the question I want to get to before the end of the session tonight, is in a different photoelectric experiment, blue light obtained from a light bulb is shone onto a metal and electrons are released. The wavelength of the blue light, 470 times 10 to the negative 9 meters, or 470 nanometers, and the bulb is rated at 60 megawatts. The bulb is only 5% efficient. Calculate the number of photons that will be incident on the metal plate per second, assuming all the light from the bulb is incident on the metal plate. Okay, so let me show you how we break this question up. Okay, first things first, we need to calculate the energy radiated per second by the blue light. Okay, so it's only 5% efficient, so 5 over 100 multiplied by 60 megawatts, so that's 60 times 10 to the power of 3, or negative 3, sorry. Not megawatts, sorry, I meant to say milliwatts, so it's 10 to the negative 3, sorry, I'm so stupid. That is equal to 3 times 10 to the negative 3 joules per second. Okay, the energy dissipated per second, or radiated per second. Now we know that the energy obviously is equal to HF, but frequency is equal to C divided by lambda. So we're going to combine it to say, therefore, E is equal to HC all divided by lambda. Okay, so this will equal to, of course, 6,63 times 10 to the power of negative 34 multiplied by 3 times 10 to the power of 8. Rule a straight line because it's a longer text over the wavelength, which is 470 times 10 to the power of negative 9, and therefore the energy of the photon will be equal to 4,232 times 10 to the negative 19 joules. Okay, now we want to find out what is the, so we got the energy as well as we got the energy for efficiency. And the question in 10.2.1, calculate the number of photons. Okay, so the total number of photons incident per second. So let's just say number of photons, just to shorten all that text there, is equal to the energy radiated per second, which is 3 times 10 to the negative 3, all divided by the energy of a photon, which is 4,232 times 10 to the negative 19. That'll give us the number of photons emitted, 7,09 rounded off, times 10 to the power of 15 photons. Okay, you don't have to add this in because it's just a number. There's no numerical value. Okay, that's 10.2.1. All done. Okay, so we had to first calculate the energy per second. It was 5% efficient. Okay, but the blue light is only 5% efficient of the bulb. Okay, find out if of that 5% efficiency, calculate what would the energy be of a photon. Okay, and then calculate the total number is with that energy that this blue light provides. Okay, and it's 5% efficient. How many would be emitted? 7,09 times 10 to the 15 photons. Okay. The question after that was, without any further calculation, write down the number of electrons emitted per second in the metal. It's the same as this answer here, 7,09 times 10 to the 15 electrons. It's the same question. Okay. It's the same thing. Because photons, photoelectrons, same thing. Which that wraps up our evening of all our sessions. Also wraps up photoelectric effect. We only revisit this again once we revise it for the final exam. This is closed. Okay, next week we do some revision for the mock exams coming up now in September. So we'll take it section by section from next week. All right, please don't forget to like, comment, and subscribe to our channel. Good, better, best online videos, and we will see you next week Wednesday.